Welcome to this short tutorial for ReliaCalc, the reliability engineering calculation software. I'm just going to go through how to use ReliaCalc and the basic functions of the program. So firstly, ReliaCalc depends on adding a system, which will have components inside it, and both of those aspects will be analyzed within the program. So first of all, I'm just going to add the system, and I'm just going to name it demo system. It can be named any arbitrary name that you like. And upon adding the system, you'll notice that a worksheet has been added to the right here. This is where all the components will be placed, as well as a results box down here. Now, if I went to add another system, say demo 1 system, the second system would appear, minimizing this system down here, but both would be accessible within the program. So you can work on both systems at once on the same file. So I'll just delete that second system for simplicity, open that one. Okay, now we're just going to add components. Now we'll name it components 1. Enter the uptime, which is the amount of time the component is operational. So I'll say 1,000 hours, and the downtime, which is the time that it's down for either maintenance or whatever definition the reliability engineer has. So let's say it was down for 10 hours during that 1,000-hour period. So that's the required fields filled out. Now for a further analysis, you could add these optional fields here, or the failure modes and effects analysis variables down here. But for this example, I will ignore that. So I'm going to add 1. So that's component 1, and we'll add a second component for the analysis. Let's change the downtime to 5 in comparison. Okay, so that's component 1, component 2. Now, component 2's reliability is slightly higher due to the decreased downtime. Now, finally, in the analysis, you have to add dependencies. So I'm just going to add a dependency there. So I'll make each component dependent on each other. So we have the system select. Component 1 will be dependent on component 2 within the system to function. So I'm going to apply that. You notice there's a join there, so that means component 1 is dependent on component 2. Finally, we can go ahead and solve for the reliability. So we click the solve button up here. All right, and now the whole system results for the reliability has appeared. So the whole system reliability for this setup with component 1 reliability of 99% and component 2 reliability of 99.5 depending on each other is 98.5%. So that's a very simple example of how to use the program to calculate reliability for a system. And now, upon analysis of each component, this is where the program can decipher how to improve each component to improve the overall system reliability. So I'm just going to go ahead and slide this here. So that's saying that the uptime should be increased by 15%. So all the other variables are exactly the same. The downtime is exactly the same. The component failure characteristics are the same as redundancy components, but the uptime be increased by 15%, which therefore increases the component reliability by 0.13%, and also the whole system reliability by 0.13%. So that is the analysis for each component. And you can go ahead and change everything you want. You can replace the component reliability. So if the downtime was increased and the uptime was decreased, obviously the whole system reliability will be decreased. So I'll go ahead and replace that. And the other analysis that can occur is the addition of another component. I'm just going to call it component 3 with 10 downtime there. Okay. And the way we lay these out will adjust the reliability. So now it's in a parallel formation, which basically means component 1 must function, but either component 3 or component 2 will have to function for the whole system to function correctly. So it was 97.9% the reliability, but now in this parallel formation, it is 98.39%. So it's increased it by a bit over 1% there with the parallel formation. So the reliability engineer would then have to decide whether it's worth adding this redundancy component to increase the overall system reliability by that 1% or whatever it was. So that's a simple example, and now I'll just quickly go and open up a new file, an old file that I prepared earlier. So this is an example system that I made earlier of all the possible layouts of all the information from this component window here. So I've gone and filled out all the variables, and this is what has come up with for each of these, and I've connected them all. And you can see here in the results box that the whole system has a pretty high reliability of 96.98%. And that's for the overall reliability. These different definitions are different, which you can read about in the resources section. So for example, inherent availability, there's a definition for that, etc. That can all be seen within the program. And then obviously the individual component details as well as the whole system component details. Lastly, you'll notice these are color coded. That's to do with this failure modes and effect analysis down here. So each of these three would have been filled out, and it describes the risk to the system with each component that fails. For example, component 6 here has green tinge to it. So component 6 has a very low risk. So with failure, the system will not function terribly poorly. It will show some effects, but not overly. Whereas component 13 here, component 13, you down here, you'll notice it's high risk because it's in the red. Therefore, with component 13 failing, the entire system will struggle greatly.